Today we're going to learn about logarithms and logarithmic functions. Begin by graphing the exponential function 2 to the x at right. Now swap the x and y values to graph the inverse of 2 to the x. This table represents the inverse. The inverse of 2 to the power of x is log base 2 of x. The inverse of an exponential is called a logarithm. We write that in the form log with the base written in subscript, and then the value you are taking the log of is called the argument. The inverse of y equals 10 to the x is the logarithmic equation y equals log of x. Log of a is called the common log, and its base is 10. The base of the exponential function is the base of its inverse logarithmic equation. ln a is called the natural log of a and is the inverse of e to the x. Remember, the inverse of 2 to the x is log base 2 of x. The inverse of 6 to the x is log base 6 of x. You could write this as log base 6 parentheses x or log base 6 of x. The inverse of e to the x is log base e of x. Log base e of x has a special name, the natural log of x, written as ln x. There are two important things to keep in mind. A logarithm is an operator. You are taking the log of something. This is log base 2 of x, not log base 2 times x. Similar to trig, like sine and cosine. You're not taking sine times x, you're taking the sine of x. What about when you don't write a base? When no base is written, the base is 10. Just like when you don't have a little number here, you know it's a square root. The base of the common log is 10. For exponential form, y is equal to b to the x. To rewrite that in logarithmic form, the log base b of y is equal to x. The base of the log becomes the base of the exponent. The answer to a log is an exponent, and the argument of the log is the result of your exponent. To rewrite exponential form into logarithmic form, the base of my exponent becomes the base of my log, the result of the exponent becomes the argument of the log, and the answer to a log is an exponent. Try completing this table on your own and then press play to check. For number 3, evaluate each logarithm without a calculator. We are basically asking 4 to the power of what gives me 64. Log base 4 of 64 is 3 because 4 cubed is equal to 64. For part B, log base 5 of 0.2. I would prefer to write 0.2 as a fraction because fractions can be easily represented with negative exponents. So to evaluate log base 5 of 1/5, I'm looking for 5 to the power of what exponent gives me 1 over 5. For the 5 to change from the numerator to the denominator, the exponent needs to be negative. In this case, -1. To evaluate log base 1/5 of 125, we're basically solving the equation 1/5 to the power of what is equal to 125. If I put 1/5 to the power of 3, I would get 1 over 5 cubed, which is 1 over 125. But I need 125 in the numerator, so to change the side of the fraction bar, I will make the exponent negative. This means that log base 1/5 of 125 is equal to -3. For part D, 36 to the power of what gives you 6. You did not change the side of the fraction bar. Both of these numbers are in the numerator, so our exponent needs to be positive. But the difference here is that the exponent needs to be a fraction because the square root of 36 is equal to 6, making your answer 1/2. Remember that a log with no written base has a base of 10. So this is asking 10 to the power of what is equal to 10? That would be 1. Part F is asking 64 to the power of what gives you 1? Anything to the power of 0 gives you 1. So anytime you take the log of 1, your answer will be 0. And anytime your base matches your argument, your answer will be 1. Remember that natural log is just log base e. So this is asking e to the power of what gives me 0. We know that no exponent will make this result in 0. So because the directions ask us to evaluate, this value is undefined. We would not put no solution because we're not solving anything here, we're evaluating. And it's not just undefined because this was the natural log. This could be log base anything. You cannot take any log of 0. ln of -4 is saying log base e of -4, which is asking e to the power of what is -4. Nope, we're not going to get a negative when your base was originally positive. So this is also undefined. You cannot take any log of a negative number. Recall that f of x and g of x are inverse functions if and only if f of g of x is x and g of f of x is x. Well, since we know that b to the x and log base b of x are inverse functions, it follows that when we compose one with the other, we will get x. When your bases match, exponential and logarithmic functions are inverse operations of one another and simplify to simply be the argument of the log or the exponent. Since your bases match, your answer is the argument of the log. Again, your bases match because the base of ln is e, so you're left with the argument of the log. When no base is written, we know it's base 10. So again, we have matching bases, which makes your answer the argument of the log. D doesn't have matching bases. But is there a way we could rewrite 25 to have the base of 5? 25 could actually be rewritten as 5 squared. Because I have a power to a power, I can multiply, which means my bases now match, and my answer is the exponent. Oh no, our bases don't quite match again. But I can rewrite 1/3 with a base of 3. 1/3 with a base of 3 would be 3 to the -1. After applying power to a power, we get 3 to the -x as your argument. Now that the bases match, the exponent is your answer. Here your bases match, so your answer is your exponent. What exponent is always there but we don't need to write? That would be 1, because e to the power of 1 is e. Your bases match, so the answer is your argument. The base of the common log is 10, so rewrite this as log base 10 of 100 to the x. Now can you rewrite 100 to have a base of 10 as well? After applying power to a power, you get log of 10 to the 2x. Because your bases now match, your answer is your exponent. That's how we use logarithms to undo exponentials and exponentials to undo logarithms. The parent graphs of logarithmic functions. Remember, your logarithmic function is the inverse of the exponential, so it will be a reflection across the line y equals x. Because the parent function for an exponential has a horizontal asymptote at y equals 0, and the logarithmic function is just an inverse reflected about the line y equals x, the logarithmic function will also have an asymptote, but this time it will be a vertical asymptote at x equals 0. So the domain of exponentials was -infinity to infinity, but the range was restricted from 0 to infinity. This time, because x and y values are swapped for inverse functions, the domain and range for logarithmic functions is swapped from exponentials. So the range is -infinity to infinity, but the domain is now 0 to infinity, non-inclusive. For asymptotes, we always use non-inclusive parentheses. Graph the following inverse functions on the same coordinate plane, then find the domain and range of each. We already graphed 2 to the x and log base 2 of x in the first example. Be sure your logarithmic graph does not cross the y-axis. To give a sketch for 10 to the x, I'm going to plug in -1, 0, and 1. Now swap those x and y points to get log of x. And here's our sketch of exponential and logarithmic inverses.